All right, let's get started with the lecture for today. So this week we're talking about viscosity, and I wanted to just introduce the idea of viscosity. But before we even get to what is viscosity, let's just talk about why a chef or a cook would care about viscosity. So basically, you care about viscosity because chefs and cooks care about the consistency of the food they make. This week we'll be thinking about the consistency of sauces, but we care about the consistency of a lot of different types of food, not just sauces. And here's kind of a extreme example. The bowl on the left, obviously, is ice cream. Looks great. The bowl on the right is ice cream as well. It's actually that identical ice cream that has melted. So when you think about it, the flavor, all the molecules that make up the taste is still there. It's identical in both bowls. Yet we'd be, you would be interested in eating the ice cream on the left and might be less interested in eating the ice cream on the right. And the difference between the two is the consistency. The bowl on the left has ice cream that has the consistency that we find delightful when we eat ice cream, and the watery, ice cream base on the right we find less interesting. So the consistency of food is important. Here's another example. I just did a Google search for a bechamel sauce. It's a sauce we'll talk about this week. And if you look at the picture on the left again, you get that nice, uniform, creamy white sauce. You can see really kind of holds. It's not watery. It is nicely poured over the food. On the right, that just kind of looks disgusting. It's watery and clumpy, and it doesn't look particularly good to eat, right? So it has the wrong consistency. So again, when we're in the kitchen, it's not just about the type of molecules that we're mixing together to make a food. We also care about the consistency. Is the sauce too thin? Is the sauce too thick? So how do we control those things? So that leads to the idea of viscosity. Viscosity provides insight into consistency. Why do chefs and home cooks care about viscosity? Well, because they care about the consistency of the food, because the consistency is going to determine how the food, how a fluid like a sauce coats other foods, as well as coats your mouth when you eat it. So a cook is often thinking about the viscosity of a sauce, even if they don't use that word. All right, so that gets us to what is viscosity. So let me just throw a question out to you. Which one of these has a higher viscosity? Which one is more viscous, water or honey? Now, I think most students would guess correctly, honey is more viscous, probably because they've heard that word before. And indeed it is, because viscosity represents the resistance to flow. So the faster a fluid can flow, the lower the viscosity, the less viscous it is. The slower a fluid flows, like in the case of honey, the higher the viscosity, the more viscous it is. And here's just some animation showing, a simulation of pouring some water versus pouring some honey, and you can really see how quickly the water splashes around, forms a surface, where the honey, as it's poured, still has its shape and slowly kind of falls into place because it is more viscous. A interesting experiment that's connected to viscosity is called the pitch drop experiment. This experiment is the longest running experiment, continuously running experiment. It was started in 1927, and it's still running now. So what is this thing? Well, what they did is they took some pitch, which is like a tar, kind of like a coal material, and this pitch, the picture is shown on the left here. This pitch although it doesn't look like a liquid, it actually is a liquid. It flows, but it flows really, really slowly. So they took this pitch and they put it in a funnel. And then they would see how long it would take for drops to come out the bottom of the funnel, knowing that it's going to take a while because it flows so slowly. So you can see in 1938, the first drop fell. Then, around 8 years later, the second drop fell. And this pattern has continued, although it's starting to take a little bit longer to fall. For example, in November 2000, the 8th drop fell. And then in April 2014, the 9th drop fell after 13.4 years. So based on this pattern, you could actually watch this experiment online if you're so interested. You can check out this pitch drop experiment, but don't expect to see a drop fall because it looks like, based upon this pattern, probably one won't fall until 2028. Now, this connects back to our theme of viscosity because the pitch is flowing really slowly, right? There's a large resistance to flow. It has a large viscosity. It's very viscous. And we can even quantify it. I'm not going to get into the calculation, but the viscosity at room temperature of this pitch is about 230 million Pascal seconds. Now, just to put that in comparison, the viscosity of water at room temperature is 0.001 Pascal seconds. Okay, and then here's some other common foods: milk, honey, chocolate, ketchup, mustard, sour cream, peanut butter, and what their viscosities are. So peanut butter, we know, has a high viscosity. Milk has a fairly low viscosity, and then these other ones fall in between. So a question for you, and let's see if you're able to answer it. How would you plot this data? Let's say I wanted to make a plot of these different foods and what their viscosities are. Would I use a linear scale to do this? Well, look at the variation of the viscosities. We have really small numbers here, kind of intermediate numbers here, and a really big number here. So what type of scale best lends itself to plotting these large variations in numbers? So hopefully you guessed it, but it's a logarithmic scale. So recall, our logarithmic scale is such that every tick mark is 10 times bigger. And on this scale, we can see water's way down here. We can see our honey, our ketchup, and our peanut butter in this region. And then our pitch is way up here with a very large viscosity. All right, let's get a little bit of practice at reading these scales. We did this earlier in the semester. Seems like a good time to revisit it. So if we know that the viscosity of water is 0.001 Pascal seconds, what, based upon this plot, not based upon your notes or what you remember, just based upon this plot, what is the viscosity of the honey? All right, I'll give you 10 seconds to guess an answer. Please try to come up with an answer, even if it's a guess, that's okay, and then try to back it up with a procedure of how you read this plot. All right, so here we are at water, 0.001. We go up one tick mark, that's 0.01. We go up another tick mark, that's times by another 10, so that's 0.1. Another tick mark, that's times 10. Now we're at 1. And then one more tick mark, that's times 10. Now we're at 10. So 0.001, 0.01, 0.11, 10. So we would guess that the honey here has a viscosity of 10 Pascal seconds, just based upon reading this plot. All right, so I'm going to stop here with my intro to viscosity. Hopefully that gives you some sense for what do we mean by viscosity, what is the range of values it can take on. And next, I want you to check out these experiments that were posted online trying to measure the viscosity of some everyday substances.